Good morning from Waterloo, Canada. First, I would like to thank the invitation and Raghav for the nice introduction. Okay, so today I will invite you walk through the research activities for this area for recently work we have done. So basically, I will first present the challenge and the constraints in secure Internet of Things systems. And as may you have known that NIST has called the standardization of the lightweight cryptography. So I will briefly introduce this. Then we will come to our design, our four ciphers, ACE, Spix, SpoC, and the Wedge, which are the round two candidates. Finally, I will, because those are just crypto primitives, so you have to put into the applications. Then I will show you one application in LFT access authentication. So as you may see, there's already many applications in the real world. You may have seen that some smart work home, like smart meters installed in your home. Then you have seen many of those like the RFID systems, like the wearables, watches, also the healthcare. However, you did not see those things behind those applications, because all of those will, most of applications, the data will go to the like the service cloud center. They will provide analytic services or for further service in the better way. However, those applications impose the many privacy and security problems. The reason is those devices, IoT devices, are very cheap devices compared with the general laptops and the iPhone or mobile phones. Okay, so why is it so important? Maybe you are already seeing many of those applications. Also, maybe you heard some attacks. For example, malware. So this has happened a few years ago, and they got many devices. Here I listed about the 500,000 infected devices. So basically, they got the network down, even affect the Facebook's connections. Then also have Wi-Fi attacks. So those, I think it's not really shut down the network. So those just found the more like the vulnerabilities. So this is the people found those attacks in the 2017 and the last year again. However, similar attacks we found can be launched to the 4G LTE as early as 2013. Okay, so, but what's the problem here? So basically, it is a authentication problem, because those weak devices, they using the old systems. For example, they use the Telnet. So in that case, only 60 known default password they used. So what the attacker does here, just exhaustive search. You can imagine only 60 known password. Okay, this is more attacks. Okay, so this type of attacks basically manufacture for each device, they should using different master key. However, they using one master key for all devices. So that's why attacker can just come out to break one device, then they can attack many devices. Okay, so So this is where they come, why we need the lightweight cryptography. So the reason is they are very small and have limited memory and the computing resources. And also they usually used in the very specific application domain. For example, automotive onboard unit and the EPC for those products, even in very cheap product, for example, a bottled water, and the sensors, actuators, etc. And they also using different networking protocols to communicate with back-end data aggregation and the computing servers. For example, radio frequency identification, they have two types of the protocols. One type is EPC, another is a near field communication. So this is you frequently use every day. For example, you pay for your grocery, those chip cards. And the Zigbee and the Bluetooth, mobile phone 4G LTE, currently 5G, and so on. And the Wi-Fi currently is the most popular network to support Internet of Things. Okay, then let us look at the example. For example, then if that's the internet, usually we can say the data rate is 10 gigabit per second, and the security level, maybe your key size is 512 bit. Then the implementation, we're talking about the hardware implementation. So it's possible only 200K gate equivalent, and the cost is about the $50. Then you come to the Bluetooth and the data rate decreased. Also the cost possibly $2. Then you look at the EPC and the NFC, then their rate is very small compared with internet, and also they are cheap, 1 cent. Okay, so the problem is how you can provide the security to such cheap devices. Okay. And in general, for those low-cost RFID tags, then the Sunburst rule is about 2,000 gate equivalents, which can be allocated to security functions. Okay, so this is the challenge. This is how we get into these areas. And of course, industry and the government also realize this problem. So NIST called the standardization. So basically they called in the 2018 and with deadline in the February 2019. So their scope is try to select or recommend some authenticated encryption with associated data with optional hashing functionality. Then in the first round, they have 57 submissions, then they take 56. And the second round, they eliminated some, so remaining has 32 candidates. Okay, and what is the criterion they select as a final? There's a talk given by Dr. McKay in 2020, and they emphasize the selection will based on the cryptographic maturity of the design. So basically, its maturity is the first criterion for their selection for the 10 finalists, which was announced in the March 2021. Okay, so let's look at our story. So we submit 4 ciphers. Basically, should consider just 2 different ones. However, NIST explicitly said if you have different parameters, then you have to submit as a separate algorithm. So that's why we come out as the 4 submissions. Okay. So, and the first submission is so it's 4 is the ACE, Spix, SpoC, and the Welch. But the first three basically is a similar structure, is a nonlinear feedback shift register structure. So I will get this in more detail in the later slides. Okay, so this is our 4 ciphers. And if you're interested, you can go to our website to look at in more detail. So ACE is both authenticated encryption and the hash algorithm. Okay, so this is 128-bit security, and the submitters will be Professor Mark Egger is from hardware area, and the others, you see Raghav is the main player here for crypto analysis and design. Okay, so then the second is Spix. Spix is only authenticated encryption, but of course you can use as a hash. However, if you use the hash and the security is below 128-bit, only provide 112-bit security. Okay, so this is ours. Then submitter also similar group. So those are alphabetically ordered. Okay. And the third cipher is a SpoC. So this is also an authenticated cipher, but using different mode from the Spix. Okay, and this is also can be used as a hash with 112-bit security instead of 128-bit security. And the submitters are also same group as before, which names are alphabetically ordered. Okay. And then this one is different now, is we call the wedge. Basically, we have the cipher is WG here, but we wanted to make WG as an authenticated cipher. So A authenticated cipher. So we scrap the position G and A such that we can see that as an English word. So that's the wedge, authenticated encryption. Okay, so those are the submitters. Okay, so this is our four submissions. Let us look at the mathematical structure of those ciphers. So as I mentioned, ACE, Spix, and SpoC basically using the similar mathematical structures. So this is a structure called the nonlinear feedback shift register structure. So each register here hold on a bit. So for example, if we think about the salmon and the spec was designed by a group of the researchers from the NSA in United States. So this is published in the 2013. However, this structure is not new. Like the DES, first encryption cipher standardized in NIST in 1976 has this structure. However, their nonlinear function here is a lookup table. But when they did the salmon and the spec group, when they design this cipher, they have mind for the lightweight cipher. So that's why their nonlinear function here, you see, is very simple. Just one AND gate to bitwise. So you have 32-bit is 32 AND gate here, and plus some shift. That's it. That's the, I'm sorry. I'm sorry how I can make it bigger.
There's a zoom button. There's a zoom button on the top left. If you see on your PDF reader, there's a zoom button.
Can I just stop sharing, then I re-sharing?
Yeah, you can do that. Yeah, you can do it. You can.
Yeah, maybe there. Can you see?
Yeah, we can see, but you can make it a bit big.
Oh, it's, I think I don't know what's happening here.
Yeah, that's fine.
Uh-huh.
Yeah, that's fine.
Okay. I'm sorry for this technical problems.
No worries.
Okay, so that's the design of the SEM and the SpoC. So you look at this shift number, SEM and SpoC is this shift. However, when we work on this in 2015, then we found if we use this shift, we can save not that much, but 5% of gate count from the SEM and the SpoC. So that's why we called our SEM is Simeck, because we take the design from both SEM and the SpoC. Okay, so the SpoC the design, which part we are taking basically is their key scheduling. So that's why we call our cipher is Simeck. So now in all of our design, we were using this basic block as our primitive block. Okay, so this is what we get before. So one block is a Simeck block. So we were using the two Simeck block. So this is we call the Simeck-based permutation for lightweight spongy cryptographic primitives. So we shorten as the NIST. Okay. So then from this design, then still we need using actual register when we doing the implementation. So basically is from this register, data goes to next one. So we revised it. Okay, so we revised it, we put the S boxes not here. Instead, it's before the data goes to next register. So we change like this block. So this is we call the S snip net. In this case, we can save N registers in our implementation. Okay, so in our full cipher designs, basically we're using S snip net. So those work we already published before we submitted to the NIST LWC standardization. Of course, there's still need a lot of the crypto analysis, and those I just give you a few examples, like the differential and the linear crypto analysis. So those dominated our design. For example, how many rounds we will take. So in this case, for example, for the differential properties, and this is number of rounds that we will take. So we will reach the exhaustive search is your working attacker's working node. So this is how we select the round. Okay. Then once we have those basic blocks, how we conduct the authenticated encryption, how we do the hash, then this is a spongy structure because we designed its permutation, so we can put it into any structure. So we put it into the spongy structure. So we have key coming, then this is authenticated encryption. First, we need to get cipher, but we have associated data, which just need the authenticated tag without encryption. Okay, like the networking header, those you do not do the encryption. So those come in and goes to the permutation. But we start to processing data, then you have ciphertext output, C0 and so on. Finally, you have tag generated at the end. So this is authentication, the encryption, basically encrypt, including ciphertext and the authentication tag. Then you will have hash. So hash basically is you just take your message as input, then you have hash values. It depends what the hash size you wish. Then here, then you take how many bits. Okay, so this is a general SpoC structure. Okay, so our two ciphers, Spix and SpoC. So basically, it's exactly structure of a snip permutation put into the SpoC structure. So the Spix, it's we have some change. For example, like when we do the associated data, we do not need a full round. Okay, but for the SpoC, then we added another branch. So in this case, we can using SSNIPnet 192 to provide the security level of 128 bit. So, however, this is at the hardware cost. So basically, if we get the 64-bit output, we add the 64 XOR gate here. Both Spix and SpoC does not provide the 128-bit security for hash mode. So in order to get the hash mode with 128-bit security, then we slightly modified our design. So basically, we just add one branch, one register. So if we name so becomes a 5 register now. So we named our 5 register A, B, C, D, E. Then we put Simeck SpoC at the A, C, E registers. So name ACE came out. And of course, once we add the one more register, then we need also all of the crypto analysis. Then this is also done accordingly. And the last cipher is WG in the authenticated mode, which is we call the wedge. And this is we submitted in eStream in 2005. So this, because original cipher we submitted basically very big. It cannot be used for the IoT applications. So in this design, we shrink the register to the 7-bit register. So if there's a 7-bit register and the WG permutation, also the 7-bit permutation. Okay, so this is the design. Of course, there's many mathematics here in order to guarantee the security of these ciphers. So for the WG permutation, basically we have the 7-bit register. How many stages we take? We take 37 stages in order to provide 128-bit security. And also from original WG cipher, we modified, we add, so basically for one part, we add 2 small SpoCs in order to strengthen the other crypto properties like the nonlinear narratives. Then we double those branches, so which means we have two those similar structures. Okay, so however, if we nullify those SpoCs and this branch, then we get the original WG cipher back. So this is our WG permutation or wedge permutation design. Okay. So this is the hardware implementation results. As I mentioned before, so for the network cryptography, so basically in our mind, that's the gate count matters. Okay, so ACE of course is bigger because they have larger registers. So this is about the 4,000 gate count, and the ACE Spix is about 2,600. And the SpoC has the 2 versions. Night one only have 2300 gates count. And for the wage, it's about 3000. Okay, so this is the implementation about the ciphers. And we look at more detail about hardware implementation. So basically, then if we look at the nonlinear part, so they occupy the 24% of your resource. And the big chunk is registers. So which means how many initial states you need. So this is you cannot save now, okay? However, this is which is a structure. For the ACE, it is because the nonlinear part occupied more. So there is a certain trade-off. So we still can play here in order to have better performance of the lightweight ciphers. Okay, so this is just 2 examples I show you here. So you may wondering how those ciphers, since we did not advance to the round 3, then maybe you were thinking they are died, or how is the status here? So basically, also, although this is Mark and Lucia, Lucia was a PhD student when he conducted this work. And they did this comparisons. So you look at this is ACE, this is WG, and this is SpoC, Spix. So this is throughput, and this is the count number of the gate. So we are not that bad, okay. I believe, so that's why we got several contacts from industry. They were asking what's the status of a cipher. Then I said we did not advance to the third final list. But they were mentioned that there's many places they do not use in NIST standard. For example, South America. Yeah, I'm not so sure, but we are not that bad. Okay, so this is the list, the final list, 10 of them. Then you look at, I think only this 10 jumbo not in any standard. Otherwise, most of them already in the ISO standard. Okay, so this maturity is their selection. Okay, we are not in any ISO standard. Okay. Okay, so now that's the primitive part. Now we look at the application. So you only have your cipher, what you can do. Then you have to put into the applications. So then we first look at those IoT access authentication. Of course, we also look at the data protection, but here I only show you the access authentication. So most popular one currently you see either supported by Bluetooth or Wi-Fi. Okay, so this is for the Wi-Fi, this is standard IEEE 802.1a physical layer, also the constrained application protocol handshaking. So this one basically is the TOS, is a datagram TOS. Okay, so our implementation will involve using software-defined radio, and also all of the physical layer using what's called the orthogonal frequency division multiplexing modulation in physical layer. So I will just briefly introduce to you. Okay, so for the IEEE 802.11 X four-way handshaking and the data protection. So basically, data handshaking. So this is more like the client and the server mode. So supplicant is the device and the authenticator. So then those are symmetric key authentication protocol. So this is the 4-way authentication. So after that, they will have shared key called the TK. Then they will install this shared key. Okay. Then after that, they will do the authenticated encryption. They have 2 modes. One is CCMP. CCMP is AES encounter mode. So this is for encryption. Authentication is Simeck. Another is GCMP. This also encryption is AES encounter mode, and authentication is a polynomial hash format. Okay, so this is the HTTP L2.11 for the Wi-Fi. Okay. Then second one is the CoAP. As I mentioned, you look at this is the TOS. However, it's a datagram TOS, so it's simplified. They have the 6 round, basically 3 handshakings. Okay, so I want after that, they also have shared key installed. This is because for the TOS, you could have that Diffie-Hellman RAC, also symmetric key-based authentication. So here is a symmetric key-based authentication. Okay, then since we wanted to test the performance of those cipher used in actual communications. So what is the communication module? Then we're using software-defined video. So basically, we need the 2 software-defined video. We're using USRP N210 motherboard. Okay, so 2 of those. Then the final signal is the OFDM signal. Okay, so this is what in the channel could have 2 different channels, like we did in the lab room, or we didn't done in the chamber, because it's during that time we did not have much resource. We have a chamber there, but the setup is not that easy. Okay, so this is OFDM sender in the software-defined radio. So basically, the things is each of those message block is 96 bytes when you do the transmission. Okay, so then you have 96 bytes. Then you will divide it into the 2 different branches, and either is the 48 bytes, and another you will go through. You will expand it to the 384 bytes. And the first one doing the BPSK, so which is a binary modulation. The other branch will do the quadrature phase shift keying called the QPSK modulation. Okay, so basically is when you transfer your data from your ciphertext, your format is changed. You have to change it to the physical layer communications format. Okay, so that's what I want to emphasize to you. And this is, then this part is OFDM modulation. Then how you do those modulation, you need to do the fast Fourier transform, you need to add the prefix, finally you go through the antenna. So this is finally what you transmitted. It's 880 complex symbols. So this is starting from 96 byte message, come to what you said. Okay. Okay, so this is environment. So basically this 2, one in left hand, another is in right hand, software-defined radio. And then we collected those timing to the laptop to measure the timing. Then first, this is not hardware implementation. Now we need to have microcontroller implementation. So let's come out which type of the platform we choose. Then we basically choose all those popular ones. For example, it's 8-bit, 6-bit, and 32-bit microcontroller. So for the, this is for the Spix. this ATmega or MSP or Cortex M3. So for respectively for 8-bit, 6-bit, and 32-bit. For the ACE, we only did the 60-bit and the 32-bit microcontroller. And the range, we did the similar things as the Spix. Okay, clock frequency we set in the 16 megahertz for all platforms for our Microsoft controller implementation. Okay, so here I show you the performance of our ciphers. So basically we need to test two functions. One is called the key deviation function. So this is more like the pseudorandom bit generator. So you, for example, you from 180-bit master key to generate maybe 1024-bit session keys. So that's called the key deviation function. Also the MAC in communications, we have a MAC with which means that's media access control. So that's why when the message authentication code, when we use in the physical layer communication, we call it the MINC. So that's message integrate check function. So in the four-way IEEE AO.211, then basically you need to involve two key deviation function and compute 3 MACs. So this is the total authentication time. And these two are crypto computation time. And this one is the transmission time. Okay. So the KDF, basically you do not generate a tag. And for MINC, you generate a tag. So that's what. So you look at the four-way. So that's Wi-Fi case. This is transmission time, 700 milliseconds. And but this is your authentication. So which means you're computing your MAC. So it's almost 3,000 milliseconds. Okay. And for the 6-way, for the CoAP, so this is datagram TOS, of course. The transmission time is about 1,000 milliseconds, but cryptographic computation is this. So you can immediately realize basically crypto operations dominate entire those authentication protocols. Okay, so this is the smallest one, Spix. Of course, which is similar. Only the ACE is a little bit big, but it's not that so big compared with the hardware implementation. Okay. Okay, so we did some, because it's very hard to find the public work, which we can do the comparison. But I found the Crystal Parts group, they did the similar implementation for the AES. However, this is a very old work, but you see physical layer communications, they do not change that much. So it's still relevant. For this comparison, basically, which has a better throughput than the AES 128-bit, written in C and the same 8-bit platform. Also, our execution time for the cryptographic operations also acceptable. So because we need, we did our experiment using the software-defined radio, which has the transmission rate about 17 kilobit per second. Wi-Fi's transmission rate is about in this range. So we can scale up then to get this rate. So basically, it's still within the acceptable communication requirement. Okay. So I guess this is the summary of my talk today. So I introduced you our 4 submissions. So which is the ACE, also Spix and SpoC. Spix and SpoC is 4 registers, so just without this E, and also the Wedge. Wedge is the original WG cipher in AE mode. Then it's a smaller SpoCs, 7-bit SpoCs. And we also implemented them in the LFT access authentication protocol. And we also showed that they have adequate performance. Okay, I guess, okay, so this is references I taken from our recent publications. Okay, so the first 1, 2, 3, 4, 5, 6 are about our cipher design. The last one is the application in the access authentication. Basically, we also implemented for the data protection here. I did not show you that part. Okay, I guess it's time to stop my talk now. Okay, thank you.
Thank you, Professor Gong, for such a nice talk. Okay, let's see if we have any questions from the audience. I see no questions. So while we wait for some questions from the audience, I have like few questions from my side. So yeah, in your initial slides, you mentioned about like there are a lot of constraints regarding the IoT. So when you consider the NIST competition, so what are your opinions? Like in the final list, will select only one candidate or multiple candidates?
I believe it should be multiple candidates. The reason is, you see, it's a different environment from the application, also the networking protocol. So that has to be the multiple candidates. Yeah, cannot be just a single one. It's different from the you see internet communication. Then you can have AES for all, but for the IoT you cannot them have one for all. Yeah, so that I believe that's the list they just recommend. They did not say they standardize. They just say they recommend it. Okay. Yeah.
Okay. So yeah. So we have one question from the audience. So, which one of ACE, Spix, and Wedge is your favorite design and why?
Oh, my favorite design, Wedge, of course. The reason is, you see, they are not just provide all those authentication, the encryption, and also the hash, as I mentioned, maybe not 128-bit security, instead is 112-bit security. Also, you have another feature. You can learn those other SpoCs, then you can get original WG, which the key string will have what we call the white Gaussian noise behavior. Okay, so other cipher does not have this property. So that's why that's my favorite. Okay.
Okay, thank you. Yeah, I don't see any other questions from the audience, but I still have another question for you. So yeah, so considering the physical layer, so like what could be the constraints in terms of lightweight ciphers? Like when you consider the physical layer. So when you
in the physical layer, yeah. Right? Yeah, I believe that's the message format. It's one of the constraints, because you see they all currently all is the physical layer modulation. It's called the OFDM. It's orthogonal frequency division multiplexing. So they have a format, each message block is 96 bytes. Okay, So if you do authentication, so basically you do not using all those 96 bytes. But how you do, you just padding there. This is waste. So it's I believe this part it should be considered, which has not considered before. Also, you look at our implementation. Let me see. So if you look at whatever which one is or Spix, this is transmission time. So when they process the data till the antenna stage, and this is crypto operations. So crypto operation is still the dominant factor compared with the transmission. So that's why sometimes this is trade-off. You want to compute NIST crypto bit, then you put your communication, you send in more data. How you send in more data? Basically, you do multi-round. So then this is give us another direction. How we can, so basically you could do multiple handshaking, then small messages. Yeah, but all of those ciphers, the design does not come out this functionality automatically. This is need, I think, rethinking. If we look at the communication physical layer, because they have their own format. But the crypto design never considered their own format. We also did not consider till we implement this.